Hi there. Thank you all for joining us today. My name is Jason Strawn, and I'm the co-founder and CEO of CodeUp. For the past 6 months, these graduates have been training full time to become talented data scientists. Each of them have grown to love and excel at what they do, and we hope that you'll be able to pick up on that as you watch their capstone presentations. Thanks again for being with us.
Thank you, Jason. Hi, I'm Stephen Solis, Director of Business Development with CodeUp. We're a full-time career accelerator that trains data scientists across the entire data science pipeline. And then we place them at companies like Booz Allen Hamilton, HEB, USAA, CaptureRx, and Whataburger. If you're looking for someone to dive into your data, look no further than these data science graduates. With experience in statistical analysis, machine learning, Python, SQL, Tableau, and much more, they're ready to add value to your organization from day one. In the Capstone projects you're about to see, they worked in teams as full-time data scientists to deliver actionable intelligence. To kick off our presentations, here's Team Spotiscry.
Hello everyone, my name is Bethany Thompson, starting us off with the project Spotiscry. This team project is all about the science behind hip-hop music. We wanted to find out what makes a song on Spotify a top hit, while others are left in the dust. We are the Spotiscryers, a team of data scientists, and this project is a culmination of what we've learned during our time at CodeUp. Our team consists of myself, Matthew Mays, Kwame Taylor, and Brandon Martinez. Today, I'll be going over the highlights of Spotiscry with the executive summary. Next, Matthew will describe the process we obtained and prepared the data. Then, Kwame will go over key exploration insights and recommendations. Finally, Brandon will explain our machine learning model before we tie it all together with our final conclusions. So the music industry is a big business for artists and anyone else in this creative process. Of course, with the possibility of earning big bucks comes an equal risk as well. Because it can cost thousands of dollars, if not more, to create a song, it can be devastating to release music that isn't successful. The process isn't easy either, to go from songwriting to marketing to the final release day and everything else in between. The solution to this big risk? Use the trends backed by science to get those streams rising. And our goal is to identify these trends. What causes a hip-hop song on Spotify to gain users' attention and keep it? We found these trends to include making the song explicit, having a high danceability, and featuring one or more artists. We have additional insights as well, so stick around to hear more about what makes a song on Spotify hit or miss. Now, Matthew will take it over with the process for transforming the information from Spotify to a data frame ready for exploration and modeling.
Thanks, Bethany. As for the data process we performed for this project, our first step was to get our hands on some data we could work with. Once we had the data, we moved it into Prepare, where it gets nice and neat to make exploration easier. After preparations were done, we were able to begin exploring. Often while exploring, we would see features we could make or changes to the dataset would become necessary. This would be our pre-processing phase, and we routinely went between exploration and pre-processing before we were finally ready for modeling. So, let's take a deeper dive into what each of those stages looked like, starting with acquisition. Now, as for actually acquiring the data, it was pretty straightforward. Spotify has its own public API that contains tons of data from a huge portion of their media selections. We compiled a playlist of over 6,000 hip-hop songs from many different artists, subgenres, and time periods. Then we used Python with a Spotify library to connect to their API in order to pull out some very interesting features that Spotify keeps track of for each song. These range from info on the track itself, the audio characteristics, or info on the album. All of this collected data was stored in a data frame for later use using the Pandas library. Now that we had the data, we started preparing the data for exploration. So, what makes data messy? We searched through our dataset and tried to find things like missing values, incorrect data types, and any outliers or anomalies that may have been an issue. We did our best to correct any issues that could be corrected and dropped a few that couldn't. After we cleaned the data, we thought about what would be necessary for our exploration and modeling. Through the use of the scikit-learn library, we had a lot of utility in creating new features, adjusting measurements to be more easily understood, and also following good data science practices like splitting our data into train, validate, and test sets, as well as creating scaled copies for modeling. There was one important thing we kept in mind throughout this process: our target variable, popularity. So, what does it mean that our target variable is popularity, you may be asking? Well, for this case, we use Spotify's popularity rating, which calculates a number between 0 and 100 that it gives to each track. This is calculated based on the total number of times the track has been played, weighed against how recent those plays were. This means that a moderate song that came out this year may have a higher popularity rating than some older songs that did well but have been around for a while. We found 4 distinct groups that the popularity trended towards. Most of the data fit into 2 groups: the low and moderately popular songs, ranging from 10 to 40 and 40 to 70 respectively. There was also a large group of very low popularity songs, which all had popularities of 10 or below. The last was all of the hits, or the songs with high popularities of 70 plus. Next up, Kwame will be able to give you a look into our project from the perspective of someone with domain experience, as well as guide you through our exploration.
Thank you, Matt. Next, I'll discuss the exploratory data analysis of our data, paired with my domain knowledge as a hip-hop artist and producer myself. Some of the top drivers of song popularity in this dataset are when there are featured artists on a track, when there is a low lyric-to-music ratio, and when there is high danceability as calculated by Spotify's API. On the y-axis, we have popularity from 0 to 50. On the x-axis, for featured artists, we counted songs with no featured artists and then songs with 1 featured artist or more. On the second and third plots, the x-axis is bended to low, medium, and high. There were many more songs without featured artists than with, and songs that featured artists other than the primary artist on a track did much better than songs without. It also seems that people are more willing to listen to longer songs if they include featured artists. A low lyric-to-music ratio, or speechiness as Spotify's API calls it, was more popular, and most songs fell into the low range. As for danceability, it is valued between 0 and 100, and most songs were in the mid-range. Songs with high danceability were much more popular than songs with low danceability. Each track is also assigned around 3 to 7 genres. Some are umbrella genres, such as rap, hip-hop, and pop rap, and some are subgenres, like gangster rap, escape room, and dirty south. In our data, there are 386 possible genre labels. In this bar plot, we visualize the average popularity of songs belonging to a genre, focusing on subgenres with high average popularity and at least 150 total tracks. The winner, with 189 tracks and an average song popularity of 58, is melodic rap, represented here by artist Lil Uzi Vert, who has 34 melodic rap tracks to his name. From left to right, there's an extension representing emo rap, Lady E representing vapor trap, Nicki Minaj for post-teen pop, Ludacris for trap, Megan Thee Stallion for Houston rap, Lil Jon the King of Crunk, and Lil Nas X, a quintessential artist of 2019 for his hit Old Town Road, representing LGBTQ+ hip-hop. Next, I'll demonstrate how musical composition, such as tempo and key signature, can be a valuable tool to influence a song's success, whether you are an artist, producer, or executive. In our exploratory data analysis, we found that what makes a song popular compositionally is different from hip-hop subgenre to subgenre. Since Spotify is based in Texas, I'll demonstrate our findings on Southern hip-hop, which includes Houston hip-hop, Atlanta hip-hop, and Dirty South rap. In this stacked bar plot, we visualize the number of songs in each category of popularity and tempo. Tempos 111 to 130 and 131 to 150 both have similar amounts of high popularity songs, but 131 to 150 has many more moderate popularity songs. It should also be noted that most songs in Southern hip-hop were 90 beats per minute and under, which is pretty slow. Songs with tempo under 90 beats per minute have lower but somewhat comparable numbers of high and moderate popularity songs. However, this range has more low and very low popularity songs than the other tempo ranges. So while you can certainly have a hit slow Southern hip-hop song, it may be easier to gain popularity on a faster song. Perhaps this is because pop songs, on average, are 116 beats per minute, and slower tempo songs are more often played in southern dance clubs, and not as much in other regions, reducing a song's ability to spread geographically. On this slide, we visualize the number of songs with high popularity in each category of key and mode. These two features combined is what is known as a key signature. For example, C major is one of the most common key signatures used in Western music. It has no sharps and no flats. Songs in a minor key only have 1.2 points lower popularity on average than songs in a major key. However, songs in a minor key are less common, so there could be less competition for a song there. The most common key signatures in high popularity Southern hip-hop are B flat minor, C sharp major, and D major. In summation, The musical composition elements I'd recommend to artists and producers who are looking to make a southern hip-hop hit are 131 to 150 beats per minute tempo, B-flat minor key signature, and a 4/4 time signature. Now, I'll turn it over to my colleague Brandon to talk about our model performance.
Thanks, Kwame. Our modeling process consisted of using regression analysis and feature engineering to justify the relationships between song popularity and those key features that have the most influence. In many cases, ideal variable relationships aren't always linear. We identified that a simple linear model was underfit, meaning it was unable to capture all the patterns in our data. We also wanted to be sure not to overfit by using a more complex model. Finally, we settled on a second-degree polynomial regression model that allowed it to perform well on new and unseen tracks. So why is this model relevant? Our model allowed us to determine statistical significance between song popularity and key features. This model was also able to make predictions with the smallest margin of error calculated based on how far off the actual values are from the predicted values. The polynomial regression model is actually a combination of the polynomial features algorithm and simple linear regression. Polynomial features create new variables from the existing ones. Let's take two features like danceability and energy, for example. Using a degree of 2, the algorithm will square each feature, take the combinations of them, and use the results as new features. This allows the regression model to make better connections with relationships that may not be linear or a one-to-one correlation. The polynomial features algorithm was a great tool for making connections under the hood and giving our analysis more insights to work with. Here we can see the top 10 drivers that our model ranked by their feature coefficients. As you can see, some of the features are actually combinations or the squared versions of themselves. However, not all features are created equally. Our machine learning model indicated that features like energy incite a larger increase in popularity, while exclusively speech-like tracks seem to degrade it. Now that we know that these features and their combinations are significant for determining popularity, how can we apply this to the industry? Music producers and artists can now use our model and utilize these key combinations to boost the potential to make hit songs. I will now allow Bethany to wrap it up with conclusions and takeaways.
Thanks, Brandon. So after acquiring data from hip-hop songs throughout the 80s to today, we found what features were drivers of popularity, such as a song being explicit and having featured artists. We also found that subgenres could have different drivers specific to that style of music. While our modeling phase utilized different combinations of algorithms and features, the best performing model was the additional insight into what features were key drivers. And the model with the best performance was a second-degree polynomial using 7 features from the data. We highlighted the top 5 drivers, including the 5 biggest drawbacks from the results of feature engineering. This model was able to predict popularity 6% better than the baseline that just predicted the average popularity for any given song. Now, this isn't the end of Spotify. We still want to learn more from this project by adding more songs from hip-hop and additional genres of music as well. How do these key drivers change when the music is rock or pop? Will different models perform better for different genres? We also want to incorporate time into the data to discover how long songs stay a hit before becoming forgotten. Or better yet, discover what creates a timeless classic. To end, we want to thank you all for your time today. To explore more of our analysis, check out our project from our GitHub repository here or our CodeUp alumni pages. Thank you and goodbye.
Thank you, Team Spotify. As you just saw, the Capstones are an end-to-end data science project. The teams start by identifying a problem and a dataset, forming a hypothesis, and determining stakeholders. They then wrangle real, messy data to analyze, model, and visualize in order to form actionable insights. Finally, they deliver their key takeaways and their recommendations via these capstone presentations. Because of the pandemic, they worked on this project entirely remote as full-time data scientists using Zoom for daily Scrum meetings and virtual Kanban boards. Without further ado, please join us in welcoming Team AI Learning.
Hello everyone, we're the AI Learning team. Today, we're excited to share our amazing work with you to improve the online learning experience of RID Labs. To start, we'd like to introduce the team that put this project together. The team includes Daniela Bojado, Samuel Davila, Young Lang Shur, and myself, Christopher Ortiz. Let's take a look at our agenda. First, we'll cover what RID is. Then we'll provide an executive summary, share the goal and purpose of this project, and walk you through each phase of our project pipeline. Finally, we'll wrap things up with our conclusion and future investigations. Let's begin with a brief overview of who RID is. RID is a leading provider of AI educational platforms. They provide AI-based web and mobile products that cover a wide variety of subjects, including SAT prep, language competency, and professional development. Our project focuses specifically on RID's English competency app. It prepares Korean students for the TOEIC, also known as the Test of English for International Communication. The picture of the phone on the left depicts the app. Apps such as these provide students personalized remote education. This has become increasingly important with the current pandemic, where a vast amount of learning is now done online. Let's now move into our executive summary. Our goal is to increase the effectiveness of RID's online AI tutoring platform. To summarize our project, we found that there are certain sections that students generally perform worse on. Photos and explanations boost student performance, while the impact of lectures plateaus over time. We also created a classification machine learning model that can effectively predict whether a student will answer a question correctly. Our recommendations are as follows. RID could offer 2 new types of study material. The first, a combination of lectures and questions relating to sections that students have trouble with. The second is a series of lectures that develop a student's ability to interpret English by using the context of a question when photos are not available. RID could also develop a new feature that gives students the option to view alternate questions with similar explanations for the questions they miss. Doing so would increase students' exposure to explanations, which have been shown to improve student performance. RID could also update their lectures so they have an impact on student performance throughout the course of their studies. To aid them in these endeavors, RID could use our model to predict how students will perform and tailor their content accordingly. If these recommendations are followed, we expect that RID's program will be more effective at preparing students for the TOEIC. And now, Daniela will give an in-depth view of our goals.
Thank you, Chris. To reiterate, our goal as a data science team is to increase RID's effectiveness in providing personalized online education. We did this by exploring the data to draw insights about what affects student performance. We define a student's performance as the percentage of questions they answer correctly. We also created a model that predicts when a student will answer a question correctly. The purpose of our project is to increase the quality of the remote education RID students receive. This is important because an increasing number of students are transitioning to online education in response to COVID-19. Now let's look at an overview of our project pipeline. We began by planning out our project in Trello, a project management tool. Next, we acquired our data from the website Kaggle. Then we prepared and cleaned the data using the Python libraries Pandas and NumPy. This set us up for exploration. We explored the data using Matplotlib, Seaborn, and SciPy to find the drivers of student performance. Then we used the scikit-learn library to build a model that predicts what questions a student will answer correctly. Finally, we summarized our findings and came up with a set of recommendations for RID to improve their product with. Below is a complete list of the tools that we used throughout our project. Now, let's take a closer look at how we acquired and prepared the data. Our data was stored in EdNet, the world's largest open database for AI education. We downloaded the data from Kaggle. The dataset contained around 390,000 students' performance data and was composed of over 100 million rows. To facilitate exploration, we reduced it to 100,000 students with 21 million rows. Now, let's look at a breakdown of the data structure for questions. There are 2 segments, listening and reading. Within each segment, there are multiple sections. The listening segment is composed of sections involving photographs, question responses, conversations, and narration. The reading section is composed of sections involving incomplete sentences, text completion, and passages. The screenshot to the right gives us an example of what an incomplete sentence question might look like. Let's keep the overall data structure in mind as we go forward into exploration. Next up, Samuel will talk about some of the key findings that we uncovered while exploring the data.
Thanks, Daniela. We explored the data to identify whether different variables hindered, improved, or had no significant impact on student performance. Identifying these variables is essential to not only improving our model's predictive capabilities, but also informing us about what changes RID can make to improve their system. Let's begin by exploring how students perform across each of the different sections of the learning material. Student performance was weakest on questions that involved incomplete sentences or narrations, as indicated by the 2 bars at the top of the graph. Conversely, students performed the strongest on questions that contained photographs, as indicated by the bar at the bottom of the graph. In light of these findings, we suggest that RID offers study material for their most challenging content, along with material that develops their students' ability to understand English based on contextual clues. This may help them in cases where photos aren't available. Next, let's look at how students' performance varies between questions with and without explanations. An explanation tells a student why they got an answer incorrect. The bars on the left half of the graph represent student performance in the reading segment, while the bars on the right represent their performance in the listening segment. The orange bars represent questions that did not have an explanation, while the green bars represent questions that did have an explanation. The graph shows that students perform better when given an explanation, regardless of the subject. We recommend that RID add a new feature that works as follows. When a student gets a question wrong, in addition to an initial explanation, the app also offers the student the opportunity to view a different question with a similar explanation. This would provide students with more exposure to explanations, which we know to have a positive impact on their performance. Finally, let's examine how lectures impact student performance. To illustrate this, we took a random sample of 2,000 students and picked the 3 who had viewed the most lectures among them. The colored dots in the graph depict their performances over time. The x-axis represents how many lectures a student viewed, while the y-axis represents their performance after viewing that many lectures. The graph shows that even though there was an initial performance increase for the 2 students represented by the blue and orange dots, as the number of lectures continued to increase, the performance of all the students plateaued, and there was no significant change thereafter. We saw similar results across the average performance of the 2,000 random users we originally sampled. Their performance is represented by the red line in this version of the graph. In light of this, RID could revise the content of their lectures to make them more impactful for the full duration of a student's studies. Next up, Yong Liang is going to talk about our predictive model.
Thank you, Samuel. Our best model is a light gradient boosting machine, also known as LGBM. The visual you see here depicts the top 5 inputs that impact our model's predictions. The graph shows the number of times the feature has been used in the model. Since individual performance and question difficulty are the most important inputs, we only use these 2 in our model. Now that we know what went into our model, let's review how we gauge its performance. To begin, we set a benchmark by creating a baseline model. The baseline makes random predictions as to whether or not a student will answer a question correctly. The x-axis in the graph represents a false positive rate. This is the percentage of questions that were predicted to be correct but the students got wrong. The y-axis represents a true positive rate. This is the percentage of questions that were predicted to be correct and students got right. The red area on the graph, also known as the AUC, or the area under the curve, represents how often the baseline made a correct prediction. In this case, approximately 50% of the time. The performance of our best model, LGBM, is represented by the blue area in the graph. It surpassed the baseline by 47%, which is represented by the light blue area above the red dot line. Now that we've explained how we gauged our model's performance, let's examine a simplified representation of how our model works. The model begins by asking a question such as, was the question difficult? If the response is no, the model predicts the students answer the question correctly. If the response is yes, the model then asks another question. Does the student have at least a B average? If the answer is yes, the model predicts the student's answer is correct. Otherwise, it predicts the student's answer is incorrect. After tree is complete, the model transfers what it learned to a new tree. This cycle repeats many times. Each tree attempts to reduce the errors of its predecessor. The end result is a tree that, in combination with all previous trees, improves the predictive capability of the model. Now that we've walked through our process from planning all the way to our final model, Daniela will review our conclusion.
Thank you, Yonglang. Our overall results were that students performed worse on questions that involved incomplete sentences or narration, while performing better on questions that include photos or explanations. We also found that the impact of lectures tends to plateau over time. Lastly, we created a model that predicts when a student will answer a question correctly. Our best model was created using the LGBM algorithm and produced an AUC score of 0.74, which outperformed our baseline by 47%. Our recommendations are for RID to offer more study material for the difficult sections of their program, namely incomplete sentences and narrations. They should also provide more content that strengthens their students' ability to understand English based on context clues, as this may help them answer questions when photos are not available. We also recommend that they develop a new feature that gives students the options to view alternate questions with similar explanations for the questions that they missed. Doing so could increase a student's exposure to the explanations which have been shown to improve a student's performance. RID could also revise the content of their lectures so that they have a stronger impact on students' performance over the course of their studies. Lastly, RID could use our model to predict student performance and to tailor their learning material for each student's needs. If these recommendations are followed, we expect that RID's program will be more effective at preparing students for the TOEIC. With regards to our future investigations, we'd like to adapt our model to RID's other educational programs, update it to predict student performance more effectively, and to create new models using different algorithms such as XGBoost. We'd like to thank RID Labs, Kaggle, and CodeUp for their help in our project. If you'd like to know more information or to contact us, follow us on our GitHub pages or our project website, dardencapstone.com. Thank you.
Thank you, AI Learning Team. At CodeUp, we just don't teach stats, SQL, Python, and other various tools. We teach our students how to learn and approach new problems with perseverance and self-reliance. This is what builds adaptable professionals. They can use or learn whatever tools you use to create meaningful solutions. This adaptive expertise is often referred to as learning agility, one of the most highly sought-after qualities in the tech field. As you watch our next presentation, you'll see how this group turned a problem into an innovative solution. Here's a tale of two cities.
Welcome. My name is Raven Young. Our team has uncovered some unique characteristics within the CDC's Social Vulnerability Index that will help officials not only identify vulnerable communities during a natural disaster, but also identify which vulnerability factors need to be targeted during a pandemic. First, we'll introduce our amazing team, provide a quick summary of our findings, and then take a deeper dive into how we made these discoveries. I'll provide an overview of the background and data sources. Corey Solitaire will reveal the discoveries made during exploration, and Luke Becker will explain how modeling led us to further insights. Finally, I'll summarize the impact our results can have for our community. In 2011, the CDC created the Social Vulnerability Index, known as SVI, to assist officials in identifying communities which may need additional assistance before, during, or after a natural disaster. The CDC found 15 features that predicted community vulnerability. They grouped these into 4 subgroups and used these to rank all census tracts nationally every 2 years. Scores range between 0 and 1. The higher the score, or closer to 1, the more vulnerable a community is, and the more likely it is to need additional resources during a natural disaster. The scores here are from the most recently available CDC map, and notice, only a few hundredths of a point separate the scores between San Antonio and Dallas. Because SVI was developed to predict areas that would be more vulnerable during a natural disaster, we expected it to be a good indicator of pandemic impact in San Antonio and Dallas. Instead, we found that it's okay at predicting pandemic impact in San Antonio, but not at all for Dallas. And for both cities, using other key features like socioeconomic indicators, improve prediction accuracy. We recommend targeting resources based on socioeconomic need, exploring additional cities to determine how predictive SVI is more broadly, and investigating underlying differences between cities that make SVI more or less predictive. COVID-19 is the first pandemic type of natural disaster since the creation of the index. This led us to our two key questions. Is the Social Vulnerability Index a good predictor during a pandemic? And are there specific features that are more predictive than others? To our knowledge, this is the first investigation of these specific questions. As a result, we had to not only identify what data we would need to answer these questions, but also where to get the data from, and how to link the separate data sources together into a complete data set. We knew the SVI was available from the CDC, and that COVID case counts were available from most cities' public dashboards. Here we ran into our first challenge. We found that the level of detail we needed in order to match the two data sets together was not publicly available. Fortunately, investigation found a table from the Department of Housing and Urban Development, which links census tracts and zip codes and also provides a percentage of addresses within the zip code that each census tract accounts for. Using Python's pandas library, we were able to allocate a percentage of cases to each census tract and then merge the separate files together, forming a complete dataset. We then cleaned the data, removing military-based tracts, and we were ready to begin exploration. Here's Corey with a summary of what we found.
Thanks, Revan. The goal of exploratory data analysis is to discover the feature or features that have the largest impact on our target variable. To turn our data into actionable insights, we leverage the power of Python and its numerous machine learning libraries. These libraries allow us to apply complex mathematical formulas to our data quickly and efficiently. For this project, we utilized pandas for data manipulation and analysis, stats models in SciPy for statistical testing, matplotlib and Seaborn for data visualization, and scikit-learn for feature engineering. Along the way, we discovered some powerful insights that led us to rethink how the Social Vulnerability Index, or SVI, should be used during a pandemic. Before taking a deep dive into the data, we first wanted to observe the relationship between SVI and case count. The scatter plot on the left represents San Antonio, and the scatter plot on the right, Dallas. In San Antonio, the data appears tightly grouped along the trend line and demonstrates a strong linear relationships. On the x-axis, as SVI approaches 1, case count begins to rise, and as SVI approaches 0, case counts begin to fall. This is what we expected to see. But Dallas looked nothing like San Antonio. In Dallas, the data was dispersed across the trend line, and the linear relationship had all but disappeared. This was a jarring observation because it suggested that SVI was not the best way to predict case counts between the two cities. This discovery presented us with our second challenge. If SVI could not predict case counts in Dallas accurately, would another feature do the job better? To determine the best course forward, we re-examined the 15 features used in the creation of the SVI and searched for any feature that shared a relationship with case count. We found only one feature that matched this criteria: socioeconomic need. When we color-coded the plots to reflect socioeconomic need, new insights emerged. The scatter plot on the left represents San Antonio, and the scatter plot on the right represents Dallas. Green represents communities where need is low. Orange represents communities where need is high. In San Antonio, a strong association was observed between case counts and high socioeconomic need. In Dallas, a similar trend between high case counts and high socioeconomic need was also observed. While it was no smoking gun, we felt as if we finally had a feature that might provide a better way to predict case counts across both cities. So, using the scikit-learn library, we combined several socioeconomic features into a socioeconomic cluster using feature engineering in order to test this hypothesis. After exploring our data, we were left with more questions than answers. Why was SVI useful in predicting cases in some cities and not others? If we combined SVI with our engineered features, would we be able to increase its predictive power? Should we forget about SVI and only focus on socioeconomic factors? Next, Luke will walk us through the third and final challenge of our project as he discusses how we used modeling to help answer these questions.
Thank you, Corey. We took the insights we discovered in our exploration and used a process called recursive feature elimination to narrow down our data and rank the features that would be the most impactful for our modeling process. RFE tests many different combinations of features and returns the ones that are the most relevant in predicting our target variable. The top features identified by RFE in San Antonio were socioeconomic indicators, change in historic SVI score, and average historic SVI score. The top features in Dallas were socioeconomic indicators and estimated poverty measures. Another challenge we faced was the initial data set was relatively small due to the limited number of census tracts within each county. To solve this problem, we used a tool in Python scikit-learn library called Leave One Out cross-validation. This produces models which are more robust at predicting our target variable by allowing us to validate the fit of our models many more times than the initial dataset would have allowed. We decided to use regression algorithms for our modeling since we are trying to predict the relationship between the social vulnerability index and COVID cases per census tract. Using Python scikit-learn library, we tested 5 different regression models, with each using 9 unique sets of model inputs. The best result was a Tweety regressor model with a mean absolute error that improved on our baseline model by 21% in San Antonio and 3% in Dallas. Without going into too much detail, a Tweety model is a form of a generalized linear model. Generalized linear models are useful when the distribution of the input features, independent variables, is not a normal distribution. These side-by-side histograms show the prediction results for the model using the top RFE features on the left and the model using only the social vulnerability index on the right. The blue outline in both charts is the distribution of cases across the city. The closer the shape of our model is to the blue outline, the more accurate that particular model is at predicting our target variable. The model on the left did better at predicting COVID cases than the model on the right. This makes sense, as the purpose of RFE is to identify features which are best suited to predicting our target variable. With Dallas, however, neither model did exceptionally well at matching the actual case count, but still, the model using the top RFE features was marginally more accurate. A takeaway from our modeling, which confirms what we found in our exploration and statistical testing, is that the social vulnerability index is not a very good method for predicting COVID cases. Still, the top component features of SVI produce a slightly better result in the case of Dallas. By using our toolkit of regression models, recursive feature elimination, and cross-validation, we were able to create a model that produces a better prediction for local officials than simply using the social vulnerability index. Now here's Raven to summarize our conclusions.
Thank you, Luke. We found the key feature for improving the accuracy of our predictions was using total socioeconomic need in both cities. SVI alone can be useful for predicting where resources are needed for some cities, like San Antonio, but not for cities like Dallas. We recommend officials focus on total socioeconomic need scores to prioritize resources and support. Factors like households below poverty, unemployment, and no high school diploma are examples of high socioeconomic need and indicators of where resources are most needed in a pandemic. Further investigation into additional cities to determine key features could provide more insights for officials. Thank you. For more information, check out our webpage where you'll find links to our Jupyter notebooks and our interactive Tableau dashboards.
Thank you, A Tale of Two Cities. At CODA, we don't rely solely on lecture, theory, and hypotheticals. Instead, we put our students to work with raw data sets of all shapes and sizes, exposing students to ambiguity, outliers, and other imbalanced data. While many programs rely on theoretical knowledge and pre-cleaned data sets, our students have the experience of working across the entire data science pipeline, from wrangling and acquisition, planning, preparation, exploration, modeling, and ultimately delivery of that data. As you watch this next group, pay special attention to how they acquired and prepared their data. Here's Default Detection Crew.
Hi everyone, my name is Matt Knight. Our team has built a machine learning model that predicts the probability of consumers defaulting on their credit cards from an unnamed Chinese bank. We are excited to have this opportunity to share our findings today. First, we will cover who our team members are, then we will move to a brief overview of our summary and findings. Afterwards, we'll go into the data acquisition and preparation, exploration, and modeling. Lastly, we'll review insights and recommendations. Anthony is going to discuss the context of our project, as well as data acquisition and wrangling, Adam is going to talk about exploration, and Babek will cover modeling. I will conclude the presentation with insights gained and recommendations. We follow best practices in data science, using a systematic approach to guide the project from acquisition to model implementation. We use technologies including Python and Pandas, Matplotlib, Seaborn, Tableau, SciPy, IMBlearn, and scikit-learn. Here is a brief overview of our project. Our problem? A Chinese bank needs to identify customers at risk of defaulting on their credit card loans with enough time to intervene. Our goal? To develop a model that uses a customer's payment history and application data to predict loan default 6 months in the future. Our model? A logistic regression model using customers' annual income and 6 months of payment history that captures 78% of all accounts that will eventually default when tested on unseen data. Our insights? Demographic data in this data set is largely not predictive, and most demographic data should not be used to avoid unethical discrimination. And lastly, our recommended use is to flag accounts that are at risk of default for intervention and retention. At this time, I will hand it over to Anthony to further discuss the background of the project as well as data acquisition and preparation.
Thank you, Matt. In the last 5 years, the number of credit cards issued each month in China has exploded from around 450,000 in January of 2015 to around 711,000 as of September of 2020. Along with it, the amount of credit card debt has risen to 2.7 trillion US dollars, or an 87% increase since 2016. Yet, the penetration of credit cards in the Chinese market is low, especially when compared to its neighbors, as you can see on this chart with Hong Kong and Taiwan versus China. This means there's still plenty of room to grow. But with rapid growth comes risk. In this chart, we have highlighted recent periods in US, South Korean, and Hong Kong history where rapid expansion in household debt has preceded deep economic recession. There's little reason to assume the Chinese market will be any different. As such, it is of great importance for each credit card issuer to be able to predict when customers may be approaching default and intercede. In order to accomplish this, we set out to take over 430,000 credit card applications and pair them with over 1 million payment records. We accomplished this through a process we in the industry like to call data wrangling, using Python and Pandas to get the data into a format that was useful for analysis. First, we had to identify which credit card holders had at least a year's worth of payments records before defaulting. After these users were identified, we saved their first 6 months of payment history to create a blind period in order to determine if a user may default 6 months into the future. Afterwards, we grabbed the most recent year's worth of records from all the users who didn't default and ignored their most recent 6 months of records to closely mirror the defaulted accounts. Finally, we merged these users with their credit card applications to produce a single table of data where each row represented a single credit card user and each individual column represented a piece of application data, a month's worth of credit card payments, or whether or not a user defaulted. From this table, we were able to derive a user's risk score based on their 6 months of payment records, where the higher the score, the higher the risk. All this work not only allowed us to find patterns and build a model that could successfully identify a user would default 6 months into the future, but also allowed us to explore the data and gain additional insights. And with that, I'll hand it over to my colleague, Adam Gomez.
Thank you, Anthony. With the data now prepped, our next step was to do a deep dive in order to really understand who these customers were. Our application data had a lot of demographic information like gender, age, occupation, education level, and so on. With gender, we found that women outnumbered men 2 to 1. And when we compared the genders with each other, statistical testing confirmed that men were more than 2 times as likely to own a vehicle than women, while women were slightly more likely to own real estate. There were many examples beyond this, but the reason why we're focusing on this one in particular is to demonstrate the importance of really understanding your data in order to avoid unethical discrimination. For example, if we use car ownership as a means to make credit decisions, we're effectively using gender. And this should absolutely be avoided. For this reason, we focused more heavily on the payment record of our customers, and here we ran into a different kind of problem. Multicollinearity describes when 2 or more variables have so much in common that their predictive power overlaps with each other. We had built an array of features all based off of payment record, and so there was a lot of overlap. We used variance inflation factor to identify features that still had good predictive power, but that didn't correlate with each other too strongly, and we found 4 really good ones. Income amount represents the customer's total yearly income. And while this is demographic data, a customer's income is so closely tied to their ability to repay debt that there is a case for its use. Months with no balance represents the number of times that a customer did not have any debt with the bank. And months with balance paid represents the number of times that a customer zeroed out their debt by paying the balance in full. Total late payment score represents the degree by which a customer was late in making their payments during that 6-month window. Exploration into these factors found some surprising details. Customers who default had higher incomes, not lower. They also had fewer months where they had no debt, and there were 0 instances where they paid off their balance in full. This didn't happen once. They also had a higher total score. With these factors identified, we passed them on to our modeling phase, and Babek will talk about that part.
Thank you, Adam. During exploration, we had identified the following factors as driving the defaults: total score, annual income, the number of times a user paid off their debt, and the number of times a user had no debt. We then used these features to build and train our model. Our data was already divided into train, validate, and test data sets. Models are trained on a trend set, their results are validated with a validate set, and then the test set is used as unseen sample data to check how their performance will compare to a real-world data. But we realized we had class imbalance problem in our data. Class imbalance occurs when observations within one class are far less than the other one. In our case, the number of customers who defaulted on their loan was much smaller than those who did not. Modeling without balancing the data can lead to models favoring the majority class, which may lead to misleading predictions. So we used various under and oversampling methods such as random oversampling, random undersampling, and a synthetic minority oversampling technique to balance the classes, and then moved on to modeling. Since our goal was to identify customers who may default, we needed a model that can classify customers into either being defaulting or not defaulting classes. These types of models are called classification models. Classification models work by using independent variables to predict the class each observation falls into. In our case, the model will take information from these variables and use that information to predict whether a customer will default on their loan 6 months in the future. For this problem, we chose to run logistic regression, stochastic gradient descent, and rich classifier regression models. Don't let the name intimidate you. The end goal of all of these models is to predict whether a customer will default or not. They just have a different way of getting there. To measure these models' performance, we used recall score. Recall score is simply the percentage of correct predictions of a positive class versus the total of the actual positive class. In our case, how many customers our model said defaulted on their loan versus how many customers actually did. After training and validating, we're able to pick our top model, logistic regression model. So how does this logistic regression model work? It is a linear method, but at the core of the method, the predictions are transformed using the logistic function, also known as the sigmoid function, hence the name logistic regression. When graphed, logistic function takes a S-shaped curve that can take any real valued number and map it into a value between 0 and 1. Our logistic regression model was able to predict with a recall score of 78%, meaning if 20 customers out of 10,000 default on their loan, our model will be able to correctly identify 16 of them. Now, I'll pass it over to Matthew, who will go over insights and recommendations.
Thank you, Babek. To summarize, after working with both application and credit history data, we found that our application data wasn't entirely useful for predicting customer default. We recommend that the bank collect different information during the application process to be more in line with global industry standards. However, we were able to create a model that considers the cost of implementation by reducing the number of flagged accounts that are not at risk of default. The next phase of continuing this project would be to obtain more information in order to determine a customer's profitability, such as the balance a customer carried and their interest rate, and use recursive feature elimination, which systematically compares the relative predictive power of each variable to optimize the features selected for modeling. If you would like to see more detail regarding our project, please refer to the alumni portal. Thank you and have a great day.
Thank you, Default Detection Crew. From working in teams to presenting complicated data, communication skills are paramount in this day and age of a remote-first world due to the pandemic. Understanding and interpreting data is only half the story. Articulating the story that data represents requires an additional skill: storytelling. Data scientists need to effectively convey their recommendations to stakeholders, and this was one of the most top desired skills that we heard from our interviews of employers. Consequently, it was also one of the hardest ones to find. Our students gain experience delivering their data in different formats like technical report notebooks and slideshow presentations. Our final team is excited to share their story of their data. Please join me in welcoming Fourth and Four.
Good afternoon, ladies and gentlemen. My name is George Arredondo, and I'm one part of a 4-member data science team, Fourth and Four. Today, we'll be going over our analysis of the NFL Big Data Bowl 2021. We took a Kaggle dataset containing AWS Next-Gen stats of the 2018 regular season to create a machine learning classification model to understand defensive success in stopping a completed pass. Sit back and grab some popcorn as we dive into the game. For the agenda today, we'll be going over our outstanding team, followed by a high overview of our project summary. Then we'll talk about the data, how we explored the data to find insights and statistically important features to use in our model. We'll then go over our model, the performance, and finish off with conclusions and recommendations. Our team is composed of 4 amazing data scientists. First, we have Austin Aranda, then myself, George Arredondo, followed by Angel Gomez, and finally, Gilbert Noriega. Football is a true team sport that requires constant communication and both mental and physical strength to overcome the opposing team. Offenses often get the glitz and glamour when it comes to winning a game, while defenses often get overlooked. Our team will be looking at the stats from the 2018 regular season to create a machine learning classification model of how defenses can be successful in stopping a completed pass. Our best model used both existing features and engineered features that allowed us to predict a pass stopped with 95% accuracy. Throughout this presentation, our team will explain the process we went through to accomplish this. For the acquisition and preparation of our data, we first went to Kaggle.com and downloaded all the CSV files. We then converted all these CSV files into data frames using pandas. We condensed 20 data frames into one and iterated over 18 million rows of data to end up with around 250,000 to understand both offenses and defensive personnel, formations, and how plays play out from start to finish. We created dummy variables for categorical values to better visualize and understand plays. And finally, we created .py files so that we could seamlessly traverse through the data and allow it to be easily reproducible. To create a model, we first needed to define a target variable. For our project, we defined success strictly on the defensive end, whether or not a defense will be able to stop a pass causing an incompletion or interception. Now, there are a lot of moving parts to stopping a completed pass, so we had to create a plan and ask questions to accomplish this goal. Questions like, does an offensive formation influence the success of a defense? So will a defense defend better against the pass when there are more receivers, tight ends, or if the quarterback is in shotgun or under center? On the contrary, is there a defensive formation that is more successful in stopping the pass? When you have 4 defensive backs as opposed to having 5 or 6, 3 linemen or 4 or 5? We asked what characteristics make a good defender in stopping a pass? Is it speed, acceleration, a combination of both? The distance a defender is away from the receiver catching the ball? Does the defensive line play a part in stopping the pass if they apply pressure to the quarterback and the quarterback has to scramble out of the pocket? Next, we'll have Angel go over the data exploration to answer some of these questions.
Thanks, George. One of the first things we did was rank the teams by total passing yards to determine if better offenses are harder to defend. The Tampa Bay Buccaneers came in with the highest yardage, followed by the Pittsburgh Steelers and then the Atlanta Falcons. This was done to determine if a team's offense had an influence on the success of the defense, which the data proved to be true. From there, we asked ourselves, are passes stopped dependent on the offensive formation? So we gathered the offensive formations that had the highest incompletion rate among the other teams. The shotgun offensive formation, where the quarterback receives a snap 5 to 7 yards behind the line of scrimmage, had the highest in both incompletions and completions. This was followed by the single back formation, where there was one running back lined up 5 to 7 yards behind the quarterback, and coming in third was the empty formation, where the backfield is empty. Even though the formations had a different amount of complete or incomplete passes, the rate at which a pass was stopped stayed consistent across the offensive formations. One feature we used that proved useful in our models was the EPA, which posed a question: are passes stopped dependent on the EPA? The EPA, or expected points added, is a football statistic that uses historical data to predict the points added per play based on the offensive field location and prior play yardage gained or lost. From there, we determined if incompletions correlated with the EPA, which in fact proved to be true, that a relationship does indeed exist. By asking ourselves, what are the top defensive positions for stopping a pass? We explored the data a bit further and noticed there were definitive key defensive positions that had a major influence on incompletions, with the cornerback having the most incompletions, followed by outside linebackers and then free safeties. Looking at the top 3 key defensive positions for block passes, we were able to look at key attributes that make up a successful defensive player. Starting with cornerbacks, successful players were 23 years old, were 5'11" tall, typically weighed around 190 pounds, with 19% coming from Ohio State University. Outside linebackers were typically 25 years old, were 6'3" tall, weighed around 250 pounds, with 24% coming from University of Georgia. And free safeties were typically 27 years old, were 5'11", weighed around 205 pounds, with 19% coming from the University of Utah. Now I'm going to pass it to Gilbert to share our insights on successful defensive formations and player tracking data.
Thanks, Angel. Since we know what position is most responsible for stopping the pass, we started to ask ourselves, is there a defensive formation that is better at defending the pass? On the screen is 4 examples of what a defensive formation could look like, with the offense represented by a black X and the defense represented by a red circle. The exact location is not what defines a defense, but rather how many defenders in each position there are. After some statistical testing, the data showed that the dime formation is most effective. This helps solidify our findings about which position is most responsible for stopping the pass, because in the dime formation, there are 6 defensive backs, as represented by the bigger red circles. As you look to the right, you can see that there are 5 defensive backs in the nickel formation. And if you look on the bottom of the page, you can see that there are 4 defensive backs in the 3-4 formation on the left and the 4-3 formation on the right. The graph on the right shows the percentage of passes stopped by defensive formation. If we take a look at the graph, the dotted line represents the league average of passes stopped with 35%. The data shows that the dime formation, highlighted in red, is better at stopping the pass than all other formations. This makes sense, since because the more defensive backs or defenders in coverage, the more likely the defense will stop the pass. In the next phase, we started to focus on the most daunting part of the project, the player tracking data. The videos on the next 2 slides were created using animation library from Matplotlib and real data points from the 2018 NFL season. They will show examples of the difference between a good defense and a bad defense. In this video, the offense will be the orange dots and the defense will be the yellow dots. The colored arrows will show the orientation of the player, and the black arrows will represent the speed of players traveling. In this video, we will focus our attention to the middle of the field at orange player 41 and yellow player 54. Before the play starts, the offense on the left is in prime position to score a touchdown. As the play develops, orange player 41 runs his route up the middle of the field with yellow player 54 sitting and watching the quarterback. The quarterback tries to throw a quick pass into a small window and ends up being a costly mistake. The yellow player 54 kept a close distance to the intended receiver and not only stops the pass from being completed, but also used his speed and quick reaction time to run the interception back all the way for a touchdown. What was supposed to be 6 points for the offense turned into 6 points for the defense. In the next video, we will focus our attention to the top of the screen at orange player 24, orange player 31, and yellow player 10 near the 40-yard line. The yellow players on the right are the offense, and the orange players on the left are the defense. At the start of the play, yellow player 10 is heavily covered at the line by orange player 24. As the play develops, there was some confusion on defensive assignments, which left the yellow player 10 wide open at the top of the screen near the 45-yard line. Since the offensive line was able to pick up the blitz, the quarterback was able to identify this misstep, throw a complete pass, and let the receiver use his speed to run it for a touchdown. After reviewing similar plays across the 2018 NFL season, we had enough information across the multiple data frames to create some new features. I will now hand it over to Austin to talk about feature engineering and modeling. Austin?
Thanks, Gilbert. During our feature engineering process, we wanted to reimagine the data in a way that could be used to improve our models. Closest distance, time since last position, and QB under pressure provided some of the most valuable insights. Quarterback under pressure converted the dropback types to a simple yes or no answer. If a QB was not designed to scramble or run on that play, then he was under pressure and forced to run. Time since last position was derived from dividing the distance column by the speed column to return the difference in time between each point. This would later account for reaction time. Defensive formation assigned names to each formation based on the amount of defensive backs that were present during the play. Lastly, closest distance was a column created to define which defender was intended for the receiver who was throwing the ball. This was very beneficial for not only the model, but in defining the best defenders. During the modeling phase, our random forest model had performed the best with 93% accuracy on validation. However, after feature engineering and research on gradient boost method, gradient boost outperformed random forest by 2%. Although gradient boost is more accurate, it does come at a cost of computation. Gradient boost would take several minutes to run, whereas random forest takes up to about a minute. Keeping this in mind, we have provided a most accurate model and a most cost-effective model that will slightly lose accuracy to offset that gain in speed. The top features were EPA, which as discussed earlier, is the current statistical algorithm used by the NFL today to predict the amount of yards an offense should lose or gain based off of previous plays. Closest distance, closest X and Y points on the field, how many yards to go until a touchdown, time since last position, and the direction orientation. Given that our model performed with 95% accuracy, we wanted to measure our predictions. Majority of the time, our model was very good at predicting when a pass would be complete or incomplete. But there were a few times that our model predicted an incomplete pass and it was actually caught, and vice versa. We determined this was where the DeAndre Hopkins and Marlon Humphreys of the NFL live, the moments in football that cannot be explained by data because some players just have that X factor. We created this visual to better understand the gradient boost model. It begins by trying to answer one basic true or false question. In this case, was the pass stopped? Then what the model will do is it will iterate through a series of randomly selected true or false questions and come to a conclusion of what the model concludes as a stop pass. If we look from left to right, every iteration through our model will become clearer and clearer, asking hundreds and hundreds of questions until it reaches the best series of questions to answer and in what order. After reaching its highest point of clarity, the model will be able to accurately predict if a pass will be completed or stopped by a defense. In conclusion, our gradient boost model was accurate 95% of the time at predicting a pass being stopped. EPA and closest distance were the most significant features, and the other features provided clarity for the model to improve accuracy. The most important attributes for a defender to have is quick reaction time and proper positioning in relation to their designated receiver. When pressure is applied to the quarterback, his rate of success significantly decreases and improves a defender's odds of stopping a pass. Lastly, dime formation was the most successful at stopping a pass, but was anticipated as this formation has every potential receiver covered by a defensive back. In closing, now that we have discovered ideal defenses and their characteristics, the NFL can use our findings to better improve their drafting and scouting process for defensive backs. Our next steps would be to discover the key features for run defenses. We want to thank you for your time today, and if you're looking for your next #1 draft pick, feel free to reach out to us through the CodeUp Alumni Portal.
Thank you, Team 4th and 4. Well, there you have it. That concludes today's Capstone presentations. I want to thank everyone for joining us to see the impressive work our students are capable of delivering. If you're an employer that's interested and ready to hire a data scientist trained in all the skills that we spoke of today, head over to the alumni.codeup.com website to find resumes and contact information of the graduates you've seen today. Or if it's easier, you can just email my team at partners@codeup.com and we'll respond accordingly. Family and friends, stay tuned to see a little bit more as they reminisce on their favorite CodeUp memories and thank their supporters who helped them complete this 22-week journey. A private Zoom celebration will follow these videos.
I'd like to thank my family, both here and abroad, for their support as I begin this new career journey. Thank you to those who helped with late night Zoom calls for me to practice my projects before I had to deliver them the next day. Your feedback was greatly appreciated. Also, thank you to Stuart Rowe and Faith Kane for timely pep talk before classes even started. Encouraging me to do this now and not to wait meant all the world to me. A huge shout out and thank you to all of our instructors, Maggie, Zach, Ryan, Faith, Ravinder, John. Your pep talks and support throughout this session kept me going when things were really, really tough and gave me the confidence I needed to pursue this next career. Also, thank you to all of CodeUp support staff behind the scenes that keep things running every day and deal with things like swag bags, video editing, and headshots, and all of the other little tasks that are necessary to make everything run smoothly. To all of you, your support is greatly appreciated. Thank you.
First off, I'd love to thank my lovely wife and children for all their love and support through this journey. I'd also like to thank the CodeUp faculty and staff, especially our instructors, because without them, none of this would be possible. Last but not least, I would like to thank my peers, and specifically my Capstone team, for always being there to cheer me on. Thank you guys.
So there's so many people I'd like to thank, starting with the staff and instructors for making such a positive learning environment, and Terrell for always putting a fun riddle at the end of each survey. Then my partner, Mikalo, and all my friends and family, Caitlin, Cassia, just everyone for being so supportive of me. And last but not least, my fur baby, Twix, for always being there for me. Thank you.
I want to say thank you to so many people. I want to say thank you to my parents, my brother, my partner for working so hard to make sure I can focus on school, my best friends in my support system, Kai and Tommy. I want to say thank you to all of the instructors who have taught me so much about data science and more. The placement team, the admissions team, which I wouldn't have even picked data science had admissions not pushed me towards it. And I'm so glad that I picked it because I really love it. And I also want to say thank you to my pets, my 3 cats and my snake. They also have been great support during this time. And also thank you to all of my colleagues in Darden. Y'all have been amazing and awesome. And I love everyone at CodeUp. Thank you so much, everyone.
So I would like to thank, first and foremost, my family for being supportive of me throughout this whole CodeUp journey, especially my wife for putting up with me and everything that I've been through up to this point. I'd like to thank the CodeUp staff and especially the instructors for helping me get to this point mentally. I would have never thought it possible otherwise. I'd also like to thank my cohort for being an awesome group of people to work with and being there through all the struggles and even the wins that we've had together.
I'd like to thank my family and CodeUp for helping me through this journey.
I would definitely want to thank my family first, both in-laws and direct family. Without their support through school, I don't think I would have been able to even imagine this were possible. For sure, I want to thank my dad because he even gave my family the opportunity to come stay with him while I was going to school. So that big financial help was just what made this even an option for me to be able to do. So that for me is something I'll always remember. Also, I want to thank, my friends for even bringing up CodeUp and through their support through going through CodeUp. It's been definitely a tough challenge, but, I made it. Lastly, but not least, I want to thank, my family, my wife, my kids. Without them, they're my only motivation to even continue to better myself every day. They're the reason why I'm even here. So without them, I wouldn't be where I'm at today. Thank you.
I'd like to thank my wife, my children who helped me throughout this cohort, It was tough at times and they were always there for me, and I really, really appreciate that. I want to give a big thanks to all the instructors, Ryan, Matt, Maggie, Zach, Faith, John, Ravinder. You guys were instrumental in my success. You guys were always there to answer questions when I had them. I had a lot of questions, and I just want to thank you all for being there for me during the difficult times.
I would first like to thank the CodeUp staff and instructors for not only teaching me lessons academically, but teaching me life lessons that I can carry with me for years to come. I'd also like to thank my parents. Without their sacrifices, I definitely wouldn't be where I am today. And last but most importantly, I would like to thank my wife. Without her perseverance and support, I definitely wouldn't have been able to make my dreams come true. So to everybody, thank you.
First, I'd like to thank my lovely wife who put up with me while I was in this intensive boot camp, late nights, working all the time. Can't do much else while I was learning, and so without her support, I wouldn't have been able to complete the course. And I also like to thank the instructors for being available at multiple times throughout the day and answering questions and making sure that we all learned what we're supposed to.
Getting to this point has been challenging, but fun. And there are a lot of people that I'd like to thank. First and foremost, my girlfriend, Gina, for the daily support and encouragement that she's given me throughout this entire process. My mother for also helping me get into the program and helping me to make that decision to pursue this career. My father, he's not with us anymore, but if he had been, he would have been encouraging me every day, and I can hear his words in my mind. My friend, Matt Castillo, for supporting me during crucial moments, during special challenges that we faced as a result of the pandemic that occurred during this program. My ex-wife Amanda and my daughter Remy for also being very supportive at key moments during this program. And many others. And if I didn't name you specifically, know that there are many other people that have supported me throughout this process. I'd also like to thank my classmates for really just being a great group of people. Very supportive, very intelligent, very kind, and really helped me to grow both as a programmer and coder and data scientist, but also as a person. Thank you.
As we come to an end of this program, I would like to thank my family, especially my parents and my wife. They have provided me continuous support, and without their support, I don't think I would have been able to complete this program. I would also like to thank all of the instructor staff for teaching me all the skills that I know now. Thank you.
Hi, I just want to thank the whole CodeUp staff. It's been an amazing experience. All the instructors, career support team, admissions, everybody. It's been first class. And of course, I want to thank my family, my wife, my kids. I know it's been a sacrifice for all of us, time-wise, but I'm just very grateful. Thank you.
First of all, I would like to thank my wife and my son. Without their support, I couldn't immerse myself into a data science program and pursue a career as a data scientist. Then, I would like to thank CodeUp to help me transition into the tech field, and my instructors to help me build such a solid foundation. Finally, I would like to thank my classmates. We've been through such an incredible journey, and I've learned so much from them.
I want to say thank you to my wife for holding it down at the house while I was in the office with the door closed all day.
I'd like to thank my family and friends for always sticking with me, especially my parents who really went above and beyond as far as helping me through this course. I owe a lot to them, and they're just the best parents I could ask for. I'd also really like to share my appreciation for the CodeUp instructors and staff. I've learned so much from this experience, and a large part of that is owed to just the amazing ability of the instructors. And while I've had less direct interaction with the staff so far outside of the instructors, every encounter I've had with them has always been incredibly helpful and pleasant. And lastly, I would like to thank every single one of my fellow cohorts. You're all wonderful people, and incredibly intelligent. Getting to know y'all and go through this course together is something I'll be forever grateful for. I hope going forward that some of us have the opportunity to work together, because there's no one else I'd rather have by my side going into the workforce than any one of you wonderful people. Thank you all so much.
I just wanted to give a big heartfelt thank you to my family for their encouragement and support during this time. And also a really, really big thank you to the instructors at CodeUp. So Ryan, Maggie, Zach, Faith, John, Ravinder, thank you so much for the time and effort that you invested in me. And I'll always be grateful for that. And definitely want to thank all the staff at CodeUp as well. Stuart, for your help and as part of the application admissions process, thank you so much. And Stephen, also appreciate you and your team as well throughout the entire process. I'm very grateful. Thank you very much.
I would like to thank my friends, family, and the CodeUp staff for your unrelenting support in my journey to become a data scientist. Mom and Dad, thank you for always believing in me. Know that wherever I go with these skills I acquired, I will always honor you. Maggie, the many skills I've learned from you, thank you for teaching me proper data visualization techniques. I used to look at a chart as a chart, and information on it, it's self-evident. I mean, hey, there's a legend, right? No. You helped me realize that these visualizations are the bridge between the data and our audience. And it is my job to demonstrate its beauty, to show its truth, and to tell its story. Ryan, if I were to look at your heart, I would see a teacher, because that's the type of heart you have. Thank you for making complex concepts so easy to understand. And when we were learning many tools in a short amount of time, that makes all the difference. Zach, thank you for helping me build my first machine learning model. It was at a workshop you held where not only was I building this model, I was getting help from CodeUp alumni. And all of y'all combined made a light bulb go off in my head. Not only was I putting code together, I actually understood what the code was doing. It felt freeing, it felt exhilarating. And here we are, at the end of one story and the beginning of another. Thank you with all of my heart.
My favorite CodeUp memory was the day when Ryan said we could change our LinkedIn subheadings from student data scientist to data scientist. We had all just completed our natural language processing project, and as an entire cohort, we had kicked it out of the park. We had all finished great professional-looking presentations within the time limit, and were able to transition smoothly from one presentation to the next with no hiccups. Everyone really knocked it out of the park on those presentations, and the expressions of pride on the professors' faces when we came back to the main room was amazing to see. All of their feedback was very timely and important, but that moment of knowing that I could call myself a data scientist really stuck with me.
My favorite CodeUp memory has to be Ryan. Perpetually optimistic, helpful, and always willing to go the extra mile. Thank you for everything that you did.
My favorite memory at CodeUp is definitely hard to choose because it was a blast the whole way through, but I'll always cherish the lifelong friends that I've made along the way, and I'll also cherish all of the moments that people forgot that their mic wasn't on mute on Zoom, and I think y'all know what I'm talking about. And My other favorite memory is when Maggie told us that when the P is low, you reject, and y'all can finish that one.
I don't think I had like a particular moment that was like my favorite moment, but probably a series of moments. Just anytime we had to come up with names for any of our teams, we always just would have like a pun war and make that our names. Whoever had the punniest name, like no really punny names, that would actually be what would be the winner, I guess. We never really determined who was the best at it, but that was always hilarious to do.
My favorite memory is at the beginning of the program when we were first getting used to Zoom. We would have a lot of fun with the Zoom backgrounds, and we would just try and do something crazy and just see how long it would take for someone to notice or if they even would. And that was definitely a lot of fun.
So I have several favorite memories, and they virtually all revolve around Maggie, the senior data scientist and head instructor here in the program. And it all has to do with the hilarious use of physical comedy on our Zoom calls, whether she's kind of doing something like this on screen, or she's waving her arms around and moving back and forth. Maggie has always made key moments of our program very entertaining, and I'll never forget them.
My favorite memory in CodeUp would have to be having the opportunity to collaborate with various individuals in my cohort to produce different projects, especially my Capstone project. It was fun working with 3 other very talented and unique individuals.
My favorite CodeUp memory is working on the Capstone project with my team. Danny, Young Yang, Samuel, y'all are brilliant, and I've learned so much from you. I'm proud of the work we've produced.
My favorite memory at CodeUp was working with my Capstone team and working through our project together.
My favorite memory at CodeUp was when we had the opportunity to go to the Pearl District and get our professional headshots taken. Beforehand, the only time we really saw each other was in sweatpants or 1 inch tall on a screen. So it was the first opportunity to actually interact with the other members of our cohort and just see how tall they really were in person.
My favorite memory at CodeUp was actually getting to meet a couple of my classmates in person when I went to get a photo, the headshot. Because of COVID, we haven't been in class, and being able to meet someone face to face was actually a lovely.
My favorite memory would probably be when Maggie's and Zach's dog would interrupt class. This happened on multiple occasions. It was pretty funny. Maggie would freak out and usually get her daughter to come in to calm the dog down. And also Zach's dog would go crazy and Zach would continue lecture like nothing's going on. And eventually he would stop and go tend to his dog. So I would say those are my favorite moments.
Favorite memories from this course are almost always some form of interaction between me and my fellow cohort. The one that comes to mind most strongly is early on in the course. Me and 2 of the best friends that I've made in this time were in a Zoom meeting after class. I think it might have been some kind of casual mixture of some kind, but during it we began to play around with the Zoom background features, so we had just first discovered it. At first trying to see who could just find the funniest background, but eventually evolving into screenshotting and placing each other in each other's backgrounds. It was still early enough that there wasn't a ton of pressure, and I don't know, something about just sitting in that call, laughing and chatting with my new friends really stuck with me, and just has to be one of, if not the fondest memory of the course.
Of the several memorable moments of this remote learning journey with CodeUp, one of the top ones was finally meeting the members of my Capstone project. That was a really nice experience, finally meeting people that I've seen on Zoom for months, talking with them, getting to know them for a little bit as we did our recordings for the project.
The most memorable time in CodeUp is when I'm doing the Capstone project with my team. Chris, Daniela, and Samuel. We are the AI learning team. I enjoy that everyone in the team is mission-oriented and excellence-driven. We work together day and nights and days towards the same goal. We argue, we laugh, we bring the best of each other to accomplish our Capstone. Good luck to Chris, Danny, and Samuel. You guys are going to be great data scientists.
Favorite memory? There's been a lot. Probably what I enjoyed the most was the first few weeks of class. Myself and another student, we were going down to Geekdom, and we had our own office basically, and with a window view, and got to get through SQL together. And of course, with the pandemic, circumstances changed and we couldn't continue to go down there. But yeah, I wish we all could have done this in person. I'm a face-to-face kind of guy, but yeah, it's the whole program's been memorable.
So, in terms of favorite memory, that's a tough one because there were so many good times throughout this past 6 months at CodeUp. If I had to pick one out of a hat, there was several times where we as students were broken up into little subgroups to work on homework or work on a project. And I remember one, and it was great because most of the time we were quiet, but a lot of times we'd be interacting, talking about, hey, what does this problem mean? How do we solve this? And I remember one time there was a conversation going on about how to solve a particular coding challenge, and I remember sitting back and thinking, man, this is what you dream of doing, right? It's so cool to have this interaction with these folks, with these really great folks. So just getting to know everyone and just getting to learn alongside everyone in the Darden cohort was awesome.
Thank you for tuning in to our live stream. Employers, we hope you find a great addition to your team. Please keep in touch with me and my team and help us know which one you want to move forward with. Friends and family, take a quick break and then join us on Zoom to continue the graduation celebration. The link should be in your inboxes. Thanks again for watching.